I will still work on some problems correspond to exercise set section 16.4, but I would like to show you, this is the first time I do it and put it in my class. I want to show you how I make sure, try my best to align that the quality of my teaching is in line with the ones you get in university level, especially for the good schools you are planning to go. And here I get problems from USC. I did my PhD at USC. I didn't finish it. Okay, so I try to take a look on some USC common finals. They have common finals, means every student taking Calculus 3 will take the same final at the same time. Okay, I pick questions from their old finals, previous finals regarding relate to Green's theorem. Okay, so there will be some problems. I pick from their department final, their common final. Okay, I don't think I can finish this in the time we have, but I will do my best. Okay, I start from USC Math 226. That's their Calculus 3 at that time from fall 2011. So 13 years ago questions, given that right now is fall 2024. Okay, so in that common final number 5, the question is evaluate first directly and second using Green's theorem the line integral where C is the counterclockwise oriented triangle with vertices 0, 0, 2, 0, and 2, 2. Counterclockwise, positively oriented. Okay, you know what? I will do the greens first because I think that's easier and we can get the answer faster. Okay, so according to Green's theorem, later on the integrand will be q sub x minus p sub y. That will give us q sub x give us 2y minus 2x minus p sub y. P sub y is negative 2x minus 2y. Huh? Oh, okay. So if we combine like terms, we get positive 4y, huh? Positive 4y. Okay, now then, so this is using Green's theorem first. So the integral over closed curve of CF dot dr will be equals to double integral over domain D. This is our domain D. Okay, of q sub x p sub y dash for y dA, which is, if we describe the double integral further, 0 to 2 and then 0 to x of 4y dy dx. Is that right? That will give us integral from 0 to 2 of 2y squared 0 to x dx. That's integral from 0 to 2 of 2x squared dx, which will give us 2/3 x cubed from 0 to 2. That's 16 over 3. Okay, that's if we use Green's theorem. Now let's do the Hassel one. If we don't use Green's theorem, we do it directly. Let's call this the first path gamma 1, gamma 2, and then gamma 3. Then gamma 1. Oh, let's clarify first. Then this closed curve integral over CF dot dr is equals to integral over gamma 1 union gamma 2 union gamma 3 of f dot dr, which is basically integral over gamma 1 plus integral over gamma 2 plus integral over gamma 3 of that f dot dr. Okay, so for gamma 1, let's parameterize that first. the R1t will be, the x bit will be from 0 to 2, while the y is 0, right? Okay, now R1 prime t will be 1, 0, such that integral over gamma 1 of f dot dr will be integral from 0 to 2 of the f 5 minus 0 minus 0 comma 0 minus t squared dot 1 0 dt. Okay, this is my dr. This is my dr. This is my vector field. Okay, but after the dot product, you see that this is integral from 0 to 2 of 0 dt. That's basically 0, right? Oh no, it's not 0, it's 5. The x component is 5. 5 times 1 is 5. So, oh, okay, so this is 5 here. So that will be 10. That's for gamma 1. Let's see gamma 2. So for gamma 2, the R2t will be, the x already 2, the y will be moving from 0 to 2. So R2 prime t will be 0, 1, and integral over gamma 2 of f dot dr will be integral from 0 to 2 of 5 minus 2xy, 2xy minus y squared, comma, 2xy minus x squared dot 0, 1 dt. I plug them in first. I don't want to make mistakes anymore. Okay, and this will give us integral from 0 to 2 of, after the dot product, we will get 4t minus 4 dt, which is 2t squared minus 4t from 0 to 2. That's 8 minus 8, that's 0. Okay. That's for gamma 2. Let's see gamma 3. Gamma 3, it's parameterized by, the starting point is 2, 2, huh? So it will be 2 minus t, 2 minus t, where the t is from 0 to 2. Okay, so R3 prime t is negative 1, negative 1. And integral over gamma 3 of f dot dr is integral from 0 to 2, 5 minus 2xy minus y squared, 2xy minus x squared dot dr. Okay, I'm sorry, I need to go to the next line, but it is what it is. So I get, after the dot product, I will get, let me simplify a little bit. This is 5 minus 3 times 2 minus t squared dot, comma, 2 minus t squared dot negative 1 dt. That will be integral from 0 to 2, negative 5 plus 2 minus t squared dt, which will be negative 10 I just do it fast. Okay, I just do it fast. Plus 1/3 2 cube. Is it right? No. Yeah, 2 cube. So 8/3. What do I get there? Am I missing something again? Thomas, what happened with you? Oh, so frustrating. I hope I don't miss anything though. X, Y. You know what? Let me just do it slowly, just in case I miss something. I don't think so though. Should be cube 1/3 0 to 2 2 minus t. Ah, it should be 2 times that. This is 2 times 3 minus 1. That's 2. So I have 2 there. So this like this. Okay, now you fix it. So this will be 16/3 minus 10. But the thing is I need to put them together, right? So integral over gamma 1 union gamma 2 union gamma 3 of f dot dr will be 10 plus 0 plus 16/3 minus 10 equals to 16/3 as we expected earlier. Okay, good thing I do. That's why I do the Green's theorem first. Okay, yeah. Now let's see the second one. This is from spring 2012, Math 226 USC Common Final. The nice thing is they tell you what to use. In this case, they tell you to use Green's theorem. Okay, and if we take a look here, this is basically x squared y comma negative xy squared dot dx dy. Therefore, we can say the vector field is x squared y negative xy squared, and the q sub x minus p sub y will be q sub x, that's negative y squared, minus p sub y, that's x squared. That's basically negative of x squared plus y squared. Okay, and then the C is circle with radius 2 counterclockwise orientation. Okay, so integral over closed curve C of that f dot dr is now becomes double integral over domain D of q sub x minus p sub y dA. Now the domain is a disk, radius 2, and the integrand is nicely convertible to polar. So let me make it integral from 0 to 2 pi, integral from 0 to 2, negative r squared, r dr d theta. Independent of theta, the domain is a rectangle, right? I mean rectangle, or if we see it this way, if we see this part here, it's actually a rectangle, right? Okay, so 2 pi, and then r cube becomes 1/4, pull the negative out, r to the 4th from 0 to 2. That will be negative pi over 2 times 16, that's negative 8 pi. Oh, we are done. Huh? Too easy. Good thing they don't tell us to do it Good thing they don't tell us to do it with what's that, with to do it directly, you know. But should we try to do it directly? Give it a try. I give it a try. Okay. So this circle here, just the path C may be parameterized. No, I don't recommend you to do this. But if I do it, then it will be as follow. The path C can be parameterized by 2 cosine t, 2 sine t, where the t is from 0 to 2 pi. Okay, and then r prime t therefore equals to 2 times negative sine t cosine t. Yeah, I can factor the 2 out here. Okay, I don't know if it will do well though. So integral over closed curve of c of f dot dr now equals to integral from 0 to 2 pi x squared y, so that's 8 cosine squared t sine t, dy, dx will be negative 2 sine t dt, and then minus xy squared, that's 8 cosine t sine squared t, dy will be 2 cosine t dt. Putting things together, that's negative 16 factor out, integral from 0 to 2 pi of cosine squared t sine squared t dt. That is integral from 0 to 2 pi of power reduction formula for both. This is 1 plus cosine 2t over 2 times sine squared will be 1 minus cosine 2t over 2 dt. Okay, that becomes negative 4 outside, integral from 0 to 2 pi of 1 minus cosine squared 2t dt. Is that right? Okay, and then this is equal to, why do I get something strange again? I don't know. Because this becomes negative 4 integral from 0 to 2 pi of 1 minus 1 plus cosine 4t over 2 dt. This is equal to, this becomes 0. Yeah, with the domain of integration, this will become 0. So it becomes 1/2. So negative 4 times 2 pi times 1/2. That's just negative 4 pi, which is different from my answer earlier. What's wrong? Okay, let's check. What happened? No, it's supposed to be 32. Yeah, negative 16 minus 16, that's negative 32, no wonder. Okay, so that's 30, negative 32, negative 32, negative 32, negative 32, negative 32, over 4, that becomes 8. It's 8 already here. It's negative 8 pi. See, every time I try to do it directly, I mess up. Yeah, I try to go fast. I think that's the reason. I try to skip steps, go fast, and that's what happened. Okay, learn from my mistakes though. Okay. Next one, the next one is from fall 2012 common final. Use Green's theorem of this, where that's the F. Okay, well then what is the Q sub X minus P sub Y? Q sub X is 3Y and P sub Y is 2Y, so the difference is Y. C is the boundary counterclockwise annulus shown below. From radius 1 to radius 2. Okay, so integral over closed curve of CF dot dr is equal to double integral over region D of y dA. But that's a quarter circular annulus, so integral from 0 to pi over 2, integral from 1 to 2 of r sine theta, and then the dA becomes r dr d theta. Is it right? Okay, so that's integral from 0 to pi over 2 of sine theta d theta. I can separate this because the domain is a rectangle, all constant, and the integrand is separable. Then I can do, I can split into the product of two integrals. Okay, integral from 1 to 2 of r squared dr. The first integral is 1, the second integral is 1/3 8 minus 1, so that's 7/3. Easy. Are you sure, Thomas, this question from USC? Yes, I'm sure this is from USC. The thing is, you may think what you learned in my class is too hard, and or maybe you think it's not too hard, but it is really not too hard. It's really not too hard. We are just applying Green's theorem here. I think one of the key here is they tell us what to do. If they don't tell us this thing, then you may start thinking, okay, we have this integral, this is the vector field, is two-dimensional, and C is the boundary of a region. Now, if it's the boundary of a region, then we can just use Green's theorem. Okay, in fact, you will see in some cases later on, it may be easier to use Green's theorem as the stepping stone even if the curve is not a closed curve. Imagine if the curve here, the question here is like, oh, you need to go this way, you need to go this way, and then this way, and then this way. Suppose that's what you need to do. Okay, so what you can do is you close this first, okay, so that you can use Green's theorem. Okay, so integral over path 1 union path 2 union path 3 is equal to integral over the boundary of that domain minus integral of path number 4. Okay, but if you notice that path number 4, the orientation, if you just look at this arc here, the orientation is opposite of what we usually do. Okay, so if you reverse that orientation, that basically becomes Green's theorem, right? Minus, or if you reverse the, that becomes plus integral of negative gamma 4. Okay, because it's easier to compute the line integral over this arc here and use Green's theorem to do this, right? So instead of doing three line integrals, okay, so it may be easier for us to do single, one double integral, hopefully that's simple, and one simple line integral. Okay, that's just some ideas. If you see this recording, you will see what I meant here. But if you don't see the recording, you only see the PDF, then you will not see that idea. Okay, let's go on to the next one. Spring 2013. Let's see, be a piecewise linear path from 0, 0 to -1 and then 2, 3. So this is the first one, second one, and then back to 0, 0. Okay, this is part of y equals to -1/2 x, and is it right? To -1. And this is part of the line y equals to 3/2, I believe, x. Why do I need that? Because if this is my vector field f is this guy, comma, this guy, then my q sub x minus p sub y will become 3x squared plus 2xy. The arctangent y respect to x becomes 0, minus p sub y, but p sub y, this becomes 0, this becomes 2xy, right? Which is just 3x squared. Nice, huh? Suddenly when you use do q sub x minus p sub y, a lot of misplaced functions become 0. Okay, so according to Green's theorem, this double integral over closed curve C of f dot dr will become double integral over region D of 3x squared dA, which is integral from 0 to 2, integral from -1/2 x to 3/2 x of 3x squared dy dx. Oh, the integrand is independent of y, so I can just do the length, huh? So that's integral from 0 to 2 of 3x squared times 3/2 x minus -1/2 x. That's 2x times 2x dx. That's 6 integral from 0 to 2x cubed dx. That's 6/4, 2 to the 4th. That's 24. No, do not try. Do not try to do it with directly. I don't think so. Doing this will be pain in the beep. No. Don't do it. Please don't do it directly. Okay, use Green's theorem only. So the question is actually quite reasonable. They don't tell you what to do though. Okay, they don't tell you, oh, use Green's theorems, but the knowledge that it's two-dimensional and the path is actually a closed curve tells us that, hey, you know what? Use Green's theorem. Okay, 2013. Use Green's theorem to evaluate this. Let's see, what is the, so at least they tell us to use Green's theorem. So this is e to the x squared minus x squared y squared over 2, comma, xy cubed plus sine y. Since we will use Green's theorem, then q sub x minus p sub y will be y cubed minus p sub y will be x squared y, oh, actually minus negative. So that is actually y, I factor the y out, and then I have x squared plus y squared. Where the boundary of D, is the, well, D is the region where x squared plus y squared is less than equals to 4. So that's the disk with radius 2. Oh, and the y is positive. So we are talking about this guy here. Oh, okay. Okay, So according to the Green's theorem, it will be double integral over d of y x squared plus y squared dA. Notice that if you don't set it up properly, if you make any small mistakes there, your integration suddenly becomes nearly not doable or not even doable. Integral from 0 to pi, because it's half disk, integral from 0 to 2. Okay, the y will be r sine theta. X squared plus y squared is r squared. dA becomes r dr d theta. It's separable, integral from 0 to pi of sine theta d theta times integral from 0 to 2 of r to the fourth dr. The first integral, that's equals to 2. Well, you can do it long way, okay? But the way I think is like the integral, the area under the curve for each quadrant of sine x is 1. This is 1, this is 1. Okay, that's how I get that 2. This is pi over 2 and this is pi, right? And then the second factor, this is 1/5 r to the 5th, 0 to 2. That will be 2 to the 6. 2 to the 6 is 64 over 5. That's for fall 2013, number 7 from USC Math 226 Common Final. Problem 7. Consider a force field. That's the force field. Force field. Oh, so it may it have something to do with work, right? Okay, good. So the Q sub x minus P sub y equals to Q sub x is 2x minus P sub y is 1. Use Green's theorem to find the work by F moving particle counterclockwise along the boundary of the region enclosed by parabola y equals to x squared and x equals to y squared. Okay. So we want to deal with this region here. We will deal with this region later on. So that the work will be integral over that closed curve C of f dot dr. And according to Green's theorem, that will be double integral over the blue domain of 2x minus 1 dA. That will be integral from 0 to 1. The intersection is 1, 1, right? And then integral from x squared to x to the 1/2 of 2x minus 1 dy dx. That is integral from 0 to 1, 2x minus 1 times the length of the interval. I think you can just do it yourself from here, right? Integral from 0 to 1, 2x to the 3/2 minus 2x cubed minus x to the power of 1/2 plus x squared dx, not dy. It's dx here. Which will be 2 times 2 over 5 minus 2 over 4 minus 2 over 3 plus 1/3. You know what? Just make it positive 1/3 then. Minus 1/3. The LCD is what? 30. So 1 over 30 multiplied by 6 multiplied by 15 multiplied by 10. So -1/30. Oh, so that's the amount of work, huh? Okay. I hope I don't make miscomputation anywhere. But the principle is just like that, right? Okay, let's go on. The next one is from fall 14. The C be the triangle with vertices orient 0, 0, 1, 0, 1, 1. We saw this question earlier somewhere. Oriented counterclockwise, verify Green's theorem for vector field F -1xy by computing that integral directly and using the theorem, Green's theorem. Okay, let's do the Green's theorem by Green's theorem. Q sub x minus p sub y will be just y. Okay, so the integral over that closed curve C of f dot dr is equal to double integral over domain D of y dA. That is integral from 0 to 1, integral from 0 to x, y dy dx, which is integral 0 to 1, 1/2 x squared dx. That's 1/6. Directly, I need to do 3 paths. So suppose C is gamma 1 union gamma 2 union gamma 3. So for gamma 1, call this gamma 1, that's R1T, that's T comma 0, that's a parameterization where the T from 0 to 1. So R1 prime T will be 1, 0. So the integral over gamma 1 of f dot tr becomes integral from 0 to 1, and then -1 comma xy, x times y, oh that's 0, dot r prime 1, 0 dt, that will be integral 0 to 1 of -1 dt, that's just -1, Okay. How about the second path? The second path that r to t dx is 1, the y component will be moving from 0 to 1. So r2 prime t will be 0, 1, such that the integral over gamma 2 of f dot dr is integral from 0 to 1. The f is -1 comma xy dot 0, 1 dt. That is integral from 0 to 1 of t dt. That's 1/2. How about gamma 3? Gamma 3 will be r3t. That's from 1, 1 to 0, 0. So r3 prime t, that will be -1 comma -1. Integral over path 3 gamma 3 of f dot dr will be integral from 0 to 1. The f is -1 x comma y I'm sorry, x times y, basically 1 minus 3 times 1 minus 3, dot -1, -1 dt, that is integral from 0 to 1 of 1 minus t squared dt. This is integral from 0 to 1 minus 1 plus 2t minus t squared dt, integral from 0 to 1 of 2t minus t squared dt, that is 1 minus 1/3, is that right? Which is 2/3. Okay, so integral over closed curve C of f dot dr, basically the sum of those three integrals, which is -1 plus 1/2 plus 2/3. That's -6 over 6 plus 3 plus 4 over 6. That's positive 1/6. This time I don't make any mistake. Yay! Same with the one we did by Green's theorem, right? Okay, I think we have two more questions. Okay, let's see. So number 7, evaluate this integral where the vector field f is given by this, and C is the boundary of half annular region, where half annular region, the radius annular, radius 1 to radius 2. With y positive, so it's above the x-axis. That's what we want. Okay, so let's do what is q sub x minus p sub y. Q sub x, that's 2x, minus p sub y, that's 2y. Oh, so it's 2x minus 2y. So integral over that closed curve of the boundary of D, right? Which is our C of f dot dr. By Green's theorem, that will be double integral over D of 2 times x minus y dA. Which, if we integrate that in polar, that's integral from 0 to 2 pi. I'm sorry, not 2 pi, 2 pi only. It's from 0 to pi, not 0 to 2 pi. 0 to pi, and the radius will be from 1 to 2. 2 times r cosine theta minus r sine theta, and then r dr d theta. The domain is a rectangle and the integrand is separable. That's 2 times integral from 0 to pi of cosine theta minus sine theta d theta times integral from 1 to 2 of 1r to r, 1r, I factor the r here now, so r squared, dr. Okay, so this is 2 times 0 minus 2. So that's -2. And then 1/3, 8 minus 1. So that will be -4 times 7, -28 over 3. Okay, that's for number 7. This is the last one. Calculate the line integral in each case. So what happened is this question consists of 3 parts, part A, part B, and part C. But the part C happens to be a 2-dimensional vector field, and the curve is the circle. So because it's a circle, then it encloses, it's a closed curve, right? Oriented counterclockwise, so it's positive orientation. So let's see, q sub x minus p sub y will be q sub x negative 3x squared plus minus p sub y minus 3y squared. That's negative 3 times x squared plus y squared, while the c is the circle oriented counterclockwise, so it's positive orientation with radius 2. So that integral over closed curve C of f dot dr. By the way, do not use this closed curve notation if the curve is not closed. Okay, but if the curve is closed, you can use that closed curve notation on the integral. Okay, so this is double integral over domain D, basically the disk with radius 2 of negative 3x squared plus y squared dA, which is negative 3 integral 0 to 2 pi integral 0 to 2 r squared r dr d theta independent of theta, so that's negative 3 times 2 pi 1/4 r to the 4th from 0 to 2. That's 4, so that's negative 24 pi. Okay, that's for some of this question. Then I still have some time, huh? So let me get some more problems then. Okay, give me a second. Let me pause the recording. Okay, let's continue. I grabbed 4 more questions from that the permanent final. Actually, let me show you where I get them. Where do I get that? Hold on. You come to this website here. Actually, you can just Google it, USC Math Center, and then USC Math classes, you choose Math 226. Now, because Math 226 is multivariable calculus there. So these are the PDF link to the previous test. Okay, that's where I get them. So if you want to see more questions to study from for other than just Green's theorem, you can see there. Okay, let's see here, continue. Use Green's theorem to evaluate this for this vector field, and C is the boundary of region D lying inside the circle. Oops, what am I doing? So that is a circle with radius 1 above x-axis, and then to the left of line x equals to negative 1/2. So it refers to this section here. Are you serious? So ugly. Okay. Wish us luck. Okay, the shape of the domain is terrible. Okay, so q sub x minus p sub y will be q sub x is y cubed minus negative p sub y. So that will be negative yx squared. So I can factor the y, and then I get x squared plus y squared. I expect that though. Okay, so the integral over that closed curve. So the boundary, basically this is the boundary. This is the boundary. That's the C. Okay, we go around that path there. At least that's my interpretation. Okay, so closed curve CF dot dr equals to double integral over D of y x squared plus y squared dA. Honestly, I wonder if I want to do it. So this is integral from -1 to -1/2 for the x, and as for the y will be from 0 to square root of 1 minus x squared, y x squared plus y squared dy. Oh, it seems like it's not that bad. Maybe not. So negative integral integral -1 to -1/2 of, you know what, let me distribute the y. 0 square root of 1 minus x squared. So x squared y plus y cubed dy dx. Yeah, it's not that bad. I thought it would be very bad. At least that's not what I think right now. Okay, so this will be, the first part will be 1/2 x squared y squared plus 1/4 y to the 4th from 0 to square root of 1 minus x squared dx. That's 1/2 x squared times 1 minus x squared plus 1/4 1 minus x squared being squared dx. I think I can factor the... You can factor or you can just distribute that. I think I will just distribute it. 1/2 x squared minus 1/2 x to the 4th plus 1/4 minus 1/2 x squared plus 1/4 x to the 4th dx. Oh, 1/2 x squared cancels, right? Okay, so we have integral -1/2 to -1 to -1/2 of 1/4 minus 1/4 x to the 4th dx. Let me factor that 1/4 out. The integral of 1 minus x is x. 1 minus x to the 4th is x minus 1/5 x to the 5th. From -1 to -1/2. Then from there you compute yourself. So hard to do. Yeah, that's the interpretation of the domain though. Okay, but it turns out it's not that bad, because even though we have square root here, but all the exponents are, for the y's, are squared, right? So we can, the square root basically cancels and we have polynomials. From here we plug in numbers, I know, but not that bad, not that bad. It's doable. Next one. From 416, we have the planar region G consists of two semi-disks where the y is between 0 to square root of 1 minus x squared. That's the disk with radius 1. And y between negative, so that's a radius 2. Why it looks so ugly? It looks like that, okay. So this radius 1 and then this radius 2. Okay. Wow, if I need to do it directly, then I have how many paths to do? 1, 2, 3, 4, right? But I will use Green's theorem because the path is close, The planar region, okay. Compute the line integral along boundary of G oriented counterclockwise. So I will use Green's theorem, okay. Now, if you interpret this here, notice that this is basically x squared plus y squared to the power of 3/2 of 1, 1. Okay, that's what the notation means. So q sub x, basically that thing, do the derivative with respect to x. So 3/2 x squared plus y squared to the power of 1/2 times 2x, right? P sub y will be similar, but this time respect to y. That will give us 3x x squared plus y squared to the power of 1/2. This will be 3y x squared plus y squared to the power of 1/2. So q sub x minus p sub y will be 3 times x squared plus y squared to the power of 1/2 x minus y. Okay, so the integral, line integral over that boundary of g of f dot dr is equal to double integral over the domain g of 3 times x squared plus y squared to the power of 1/2 x minus y dA. Now the domain is actually consists of two regions. Let's call this G1. Let's call this G1. And this is G2. Okay. I use different color maybe. This is G2. Anything inside this is G2. Okay, so this is equals to double integral over G1 of 3 x squared plus y squared to the power of 1/2 x minus y dA plus double integral over G2 of 3 x squared plus y squared to the power of 1/2 x minus y dA. If we make them into polar, integrate in polar, that will be, that will be, let me move here to save some space. That's integral from 0 to 1. No, integral from 0 to pi, integral from 0 to 1, 3 r cosine theta minus r sine theta r dr d theta plus integral from pi to 2 pi, integral from 0 to 2 of the same guy. This will be, I can factor the 3 out, integral from 0 to pi of cosine theta minus sine theta d theta, integral from 1 to 2 of 1r, 2r, 3r, r cubed dr plus integral 3, integral from pi to 2 pi, integral from 0 to, sorry, I want to separate them right away. Integral from pi to 2 pi of cosine theta minus sine theta d theta, integral from 0 to 2 of r cubed dr. Okay, so this is 3 times negative 2 of 1/4 r to the 4th plus 3 times, in quadrant 3 and 4, so it's minus negative 2, so it becomes plus 2. Okay, so it becomes plus 2 of 1/4 r to the, my integral is correct. This is from 0 to 1, not from 1 to 2. 0 to 1, so this is just 1/4 here. Okay, and then that's 1/4 r to the 4th from 0 to 2. So this is the 1, 2 to the 4th. Okay, so what will that be? That's negative 3 over 2 plus 6 times 4, 24. Oh, am I right? 3. So that will be minus 1.5. So that's 22.5. Okay, I'm a bit tired. So let me just finish. How many more? 2 more. Okay, I hope that's enough. Use a method of your choice. Yeah, that's right. If you can choose, why you choose the hard one? Okay, to evaluate the work done by the force along the closed curve. So that's the hint. They don't tell you, to use Green's theorem that explicitly, but implicitly they tell you it's a closed curve. And then once it is closed curve, then in 2 dimension, then you know you can use Green's theorem. 0, 0, 1, 0, 1, 3. Oriented counterclockwise. Okay, so Q sub x minus P sub y will be 2y minus P sub y 0. Oh, that's not my mistake. Yeah, it's a function of x. I do the derivative respect to y, that's 0. Okay, so this is 2y. Good. Now then, integral, the work will be integral over closed curve CF dot dr, which is, according to Green's theorem, is double integral over d. That's the region enclosed by C of 2y dA. Then I put that in, that's 0 to 1, integral from 0 to 3, 3x I mean, of 2y dy dx. That will be integral from 0 to 1 of 3x being squared dx. That's 9. If I integrate that, well, let me just do it slowly. 0 to 1, 9x squared dx. That's 9 over 3. That's 3. Oh, just 3. Okay. Yeah, because it's 0 to 1. The integral 0 to 1 of a polynomial. Just the coefficient. That's problem 7. Let's do problem 8. Evaluate the line integral. So if we rewrite the vector field, f, that will be xy cubed plus xy, comma, 2x squared y cubed plus xy. Close piecewise linear path of 1, 1 to 4, 4 to 1, 4 back to 1, 1. Oh, this is clockwise orientation. Clockwise orientation. Okay, so this integral over clockwise orientation of C of f dot dr is equals the opposite of counterclockwise orientation, which is the opposite of double integral over region D, enclosed by that, of q sub x. Let's see, what is q sub x minus p sub y? Q sub x will be 4xy cubed plus y minus p sub y. That's 3xy squared plus xu. That's a bit ugly, huh? Don't you think so? I'm sorry, this should be xy to the 4th. Okay, so this will be 4xy cubed. They cancel. Okay. Otherwise, those are messed up. So that is equals to y minus x. Okay, not that bad. So this is y minus x dA. That's integral equals to negative integral from 1 to 4. This is 1, this is 4, and this line here is y equals to x, right? So, and then the y will be from 1 to x of y minus x dy dx. This is negative integral 1 to 4 of 1/2 y squared minus xy from 1 to x dx. Replace the y by x and 1. By x, that will be 1/2 x squared minus x squared minus, replace the y by 1, that will be 1/2 minus x dx. So that's negative integral 1 to 4 of negative 1/2 x squared minus 1/2 plus x dx. I think you can do it yourself from here on. Let me finish it up then. So that's negative 1/6 x cubed minus 1/2 x plus 1/2 x squared from 1 to 4. That's for 1 minus for 4. So that's negative 1/6 minus, what is this? So 4 cubed is what? 64, 32. That's minus 32/3 minus 2 plus 8. Ew, that's ugly. So negative 1/6. I'm so tired, honestly. So forgive me if the way I compute is strange. So that's 4 plus 3/6, that's 1/2. Okay, so that's 4.5. Okay, that's for this Green's theorem questions from USC. How many questions I did? Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Not bad, huh? Okay, I hope this way then you see that what I teach you in class and what we do, what they teach at USC, at least from the Green's theorem, is comparable. Okay, yeah. That's for now.